Nice introduction, and thank you for inviting me. So today I'm going to discuss a little bit more technical details about dynamical mean field theory and its recent developments. The important topics are exact double counting between DFT and DMFT, then stationarity of free energy functional, and final implementation of forces and structure optimization that can be done now. Most of these things you actually saw yesterday in the in tutorial. Basically, all these things are available. You just can use them for the input. Now, double counting. So, if we have two different approximations, approximation A and approximation B, all of them account for correlations to some extent. And the question is, what is the common thing in both approximations that is counted twice? And you should, of course, subtract that, doesn't it? We saw the functionals. We wrote two pieces of functionals, DFT part, DMFT part, and there is something which is counted twice. And what is that? Now, for a long time, people thought that since DMFT can be written in terms of Feynman diagrams, if I could just write approximation A also in terms of Feynman diagrams, then I know which time Feynman diagrams are counted twice, and I solve the problem. Okay? Now, what I'm going to try to argue here is that, well, if you knew Feynman diagrams, fine, then you know what you counted twice, but you don't need expansion of the functional in terms of Feynman diagrams. Just the fact that you know how the functional looks like, the approximate functional, from this you can argue what's the overlap. You don't need an expansion. An expansion is useful, but not necessary. Okay, so why is this important? Because it determines the oxidation state of the correlated ion. So the way you should think of this double counting is basically if you have some itinerant states on which the Coulomb interaction is very small, and basically in DFT we don't add Coulomb propulsion, but in general it means that they are very itinerant. The Coulomb propulsion is very small, and then you have some states on which the Coulomb propulsion is very large. Okay, and when you crank up your Coulomb propulsion, what's going to happen is that the states which have large Coulomb propulsion will shift to positive frequency, isn't it? Because you're adding bigger and bigger Coulomb interaction. Okay, so you have to subtract some of the Coulomb interaction in order to basically make them centered more or less where you started with. Why? Well, because the point is that within your other methods, approximation A, where your states were more or less aligned properly, like DFT or Hartree-Fock, there was already Hartree term accounted for. So therefore, in your next approximation, you should at least subtract Hartree term, doesn't it? And usually you have to subtract Hartree-Fock or maybe something else, and we'll discuss that. Okay, so these things are important in many transition metal oxides, in particular iron oxide, because it goes through high spin to low spin transition only if you're in the correct valence, in valence D6. If you're not in this valence, it will not go through this high spin to low spin transition, because then the system doesn't support the low spin state. So this is an example of calculation for iron oxide, in which we predicted the metal insulator transition, basically here from its isostructure or insulating B1 state goes from an insulator to a metal at high enough pressure and a high enough temperature. And that's important for the Earth core. So you can see, sorry? Mantle, thank you. Okay, so you see here the spectral function. It has a gap if you're at 0 gigapascal and 300 Kelvin. And if you're at high pressure but low temperature, you still have a gap. But if you are at high temperature and high pressure, then the gap collapses. Okay, so therefore, but why I'm pointing this out? Because I'm saying that this is possible only in D6 configuration. So if you don't have correct double counting, then your system is going to be in D6.5 typically. Usually the valence is too big, and then the physics is going to be absent.
Kristjan, is it the fact that other people who have different double counting schemes have different Venn diagram for such a system?
It happens many times. So typically, if you're using the conventional double counting, which is with anissimo, is not localized, it typically exaggerates fillings. They usually get too big fillings. And then there is another source of problems. It's not just double counting. There is this, what orbitals you pick. If you pick 1-year orbitals as your localized functions, you again typically get too large valence. Why? Because in addition, your orbital then picks not just contribution, what we call usually D, but has a lot of oxygen content. So therefore, your valence is way bigger because it's not just D, it's also oxygen. And that usually gives you the wrong valence, and wrong valence usually has wrong physics. So that's an issue. Now, the other thing which was kind of puzzling in the literature for a long time was this rare earth nickel-lights, in which it's a very interesting type of mode transition, basically where in the paramagnetic state at high temperature, you have a metal where the nickel octahedra are of the same size, but then when you go to low temperature, one octahedra, which you call nickel 1, expands a lot, and the other octahedra, every second octahedra, contracts a lot. And the one that expands, turns out, it becomes mode insulating. So this nickel 1, in which there's expanded octahedra, of course, has very small hybridization with oxygen, and therefore it's mode insulating, has high spin. But nickel 2, which is very compressed, then basically you have bonding, antibonding splitting of nickel states. They split, and you have a band gap. Now, this, of course, is hard to guess. There was a big discussion for a long time. People thought that this is charge density wave. But then eventually they realized that one can get this with so-called D8 configuration of nickel. Now, if you count valence here, what is supposed to be for nickel, you will get D7. Okay? So in D7, there is no way for such a state. Okay? You need to be in D8. And it was figured out by several groups that D8 is the right configuration, but you couldn't get it for first principle for a long time. So until the exact double counting came around, and then, well, it turns out it just comes out as a byproduct of the calculation. So therefore, I just want to point out that this double counting is not just something that is fundamentally important, but it's really practically important. Okay, so how do you figure it out what is double counting? Well, the easiest way is just look at term by term. So let's start with Hartree. Okay, Hartree is easy to understand. So we have exact functional for Hartree term is that we Coulomb interaction r minus r prime. This is just 1 over r minus r prime, and rho of r prime. Now, in typical band structure calculations, the LDA term is accounted exactly. We always do LDA in which Hartree term is accounted for exactly. While in DMFT, actually, we don't have an exact Hartree term. We have the local component of it, isn't it? The local component of it. So, but how do you get this from the exact Hartree functional to the DMFT Hartree functional? Well, the recipe is very simple. We make approximation on the functional, and we know exactly which approximation do we make on a functional, isn't it? So what do? Well, we take our charge density rho, and we project it. This projection, I showed you yesterday how it works. Basically, you just insert twice your functions, phi, whatever they are. So, but here I'm just writing this as a P on rho, which means projection. I go from the entire charge density to the local charge density. And then at the same time, I need to screen Coulomb propulsion. Now, why do I need to screen Coulomb propulsion? Some people are saying, well, let's just take unscreened Coulomb propulsion. Well, you cannot do that. Why? Because we never take into account within DMFT all the degrees of freedom. So, of course, if we account for all the degrees of freedom, including core, then you don't need to screen Coulomb propulsion. But we never do that. There is no way we can do that. I mean, right now we are usually taking one orbital or at most 2 orbitals, and all the rest is treated with mean field-like, isn't it? And all these rest of the states always screen Coulomb interaction. Therefore, we cannot use unscreened Coulomb interaction. That's different in some molecular systems where you don't have so strong screening. Sometimes you might be successful enough with just taking unscreened Coulomb interaction. For example, in H2 molecule, which we did, there you can really neglect screening because there's just one extra electron that doesn't screen much, the Coulomb interaction. But in solids, of course, at least the core states screened a lot, semi-core states screen a lot. So the Coulomb interaction always needs to be reduced. Now, and
What model of screening do you use? Like you use the DFT bands to calculate this?
basically, the best way to get decent estimation for the Coulomb propulsion is so-called constrained DMFT. So what you're doing is you're similar to constrained LDA, but you calculate the energies, total energies, with the DMFT approximation. So that's a different, decent way of estimating the screening. It's better than constrained RPA actually, because it turns out constrained RPA, which is used a lot in this area, it's usually only qualitatively correct, but not quantitatively. So, for example, with diagrammatic Monte Carlo, which we implemented recently, we saw that even in Coulomb gas, the error on the polarization is at RS is 4, which is typical metallic density. It's of the order of 400%. So it's enormous. So constrained RPA is actually pretty miserable.
So another question is, without any comparison to experiment, is there some internally self-consistent check that the screen parameters are correct or something like that? I mean, something.
Yeah, as I said, I mean, you do this with constrained DMFT, so you do self-consistently, isn't it? You calculate first your, with some U, you calculate the total energies, and then you check if you constrain the occupancy to n minus 1 and n plus 1, you check what would be the difference in this constraint in total energy for this constrained valences, okay? And that gives you Coulomb interaction. Okay, so what do we do then in DMFT? So we do two things, as I said. We screen Coulomb interaction. Instead of V Coulomb, we use V DMFT. And then instead of charge density, we use the projected charge density, isn't it? So that's the exact expression for the Hartree term within DMFT. And now, what is the double counting then? Well, the exact Hartree was already taken care of in this DFT part, and we need to subtract then the DMFT approximation for the Hartree, isn't it? So we need to take the exact Hartree functional and do the DMFT approximation on it, okay? Because LDA doesn't make approximation on it. Okay, now what about exchange? So, well, that's a different story. Within LDA, we don't take into account exchange exactly, okay? But we use so-called semi-local approximation for exchange, isn't it? So what does it actually mean? Well, we match the electron density in a solid to a density of an electron gas, isn't it? So in other words, we take our charge density rho, and we calculate what is the corresponding Fermi energy of the electron gas. Then we take the charge density of an electron gas system with this Fermi energy. That's the charge density in electron gas. Then we calculate what is exchange in this electron gas problem, okay? And, well, that turns out to be some relatively simple function of rho, as that rho to the power of minus 1/3, okay? Now, that's how we do it in LDA. Now, how do we do it in DMFT? Well, the same way as the Hartree term. So we take the charge density, we project it, and also we change the Coulomb propulsion. Now, one thing which I wanted to show you is that this expression for the exchange is equivalent to what we usually write in models, isn't it? So it's actually very easy to see. So projection on the charge density rho is equivalent to inserting these functions phi twice, isn't it? We discussed this yesterday. So insert this function phi here and here twice. That's the projected rho. Here we do the same for the other term rho, okay? And here you have Coulomb propulsion. And now you can just move this, this orbital phi here. Then you move this orbital phi here. You move this orbital phi here and this one here. And you realize that this is actually exactly the expression for matrix elements of the Coulomb propulsion. And this is basically density matrix for the charge density, isn't it? And that's what you usually write in a model calculation as the exchange, isn't it? It's the matrix elements of the Coulomb propulsion times its corresponding density matrix, okay? So indeed, this expression is written in real space, but it's exactly equivalent to what we usually write down in a model. Okay.
Just renormalizing the density interactions, right? We could have
No, no, this has everything. Sorry, this has everything. I mean, this is, sorry. You see, this has different indices, M1, M2, M3, M4. So it has Hund's in, it has F2, F4 is 6 in general. I mean, all the Slater integrals. Okay, so what is then intersection of both approximations to the functional? For the exchange, now we should be able to say. I mean, you don't need a Feynman diagram for that. Okay, you have both approximations. You start with the exact functional, you go in one route, you go another route. What is the intersection? Well, the intersection is that you need to make both approximations on the functional. Okay, in which order you do, it doesn't matter. Okay, in any order. You can first do LDA and then do DMFT on it, or you can first do DMFT and then on LDA. In both cases, what do you get? Well, you have to replace in the functional, in this functional, you replace rho with rho 0. That's because this is an LDA approximation, isn't it? Rho has to be replaced with rho 0. That's the first thing. Then Coulomb interaction has to be replaced with DMFT Coulomb interaction, because there's a DMFT approximation. And then at the same time, rho 0 has to be calculated from projected charge density, isn't it? Because that's what DMFT requires. So therefore, you need projected charge density with which you calculate the Fermi energy. Then this defines your rho 0. Once you have rho 0, you have to take into account VDMFT, and well, basically, this is the recipe. So in summary, interaction is screened in double counting term, like DMFT suggests. Then we need to use projected density in double counting term, and we need to replace the exact expression by electron gas expression. Okay? So now that we know how we do the exchange, we can do also correlations, and then we can argue what exactly the functional is. So the important point is that we don't need Feynman diagrams, because Feynman diagrams is just writing this in some type of power expansion, these functionals, isn't it? But since we know the exact form of the functionals, we know their approximation, okay? So then we can figure out what's the overlap between the two. Okay, so if we do LD approximation again on an exact functional, okay, we map the problem to an electron gas point by point, isn't it? Each point in space to a problem of electron gas with this expression. Now in DMFT, however, what we do is we also take exact phi, and then we take the Green's function, we project the Green's function to the local component, we take the Coulomb interaction, we project to the screen Coulomb interaction. And we get this expression. Okay, so we have that functional and that functional. And now we have to make both approximations at the same time. So intersection of both actually is an electron gas problem in which charge density is projected and the Coulomb propulsion is screened. Okay, so that's all there is to it. And you can write a closed expression for it. And then how do you calculate it? Well, you need to solve the electron gas problem, isn't it? Just like we did electron gas problem with the unscreened Coulomb interaction, you can also solve the electron gas problem with screened Coulomb interaction, and at the same time, you have to use only the charge density that corresponds to your correlated orbitals. And that's exactly the double counting within this approach. So the point is, we can now safely use the Cartier plus exchange correlation functional from DFT that acts on all the orbitals. Then we add the Coulomb, we add the Feynman diagrams to certain more correlated orbitals, and we know how to subtract the correlations which are accounted for in both cases. Okay, so at least in this perspective, this scheme is free of let's say inconsistencies. It's still an approximation, of course, but it's free of inconsistencies. Okay, so now stationary optimization and stationarity of free energy functional. So we have a functional we discussed many times, but before I go into this, I want to point out that, well, as we discussed many times, DFT is perhaps the best independent particle approach, which is very useful because each electron interacts with effective potential that mimics to some extent the effects of all other electrons. And the important point is we do not target the wave function, but rather the charge density or the single particle Green's function. In this case, we target the spectral function, isn't it? The two particle correlation function is almost always enough, Rarely we need to go beyond two-particle correlation function. So if you want to calculate like a neutron scattering, that's a two-particle correlation function, isn't it? While the RPS is single-particle correlation function. An independent particle approach within DFT gives total energy and charge density very well. Spectra should be unphysical, but in simple metals and band insulators, it's very, very good. Now, you probably have seen these historic pictures of how good is structure within DFT, okay? And in many times, it's remarkably good. So you look at the 4D elements, and you see that the size of so-called Wigner size cell within DFT and experimentally is almost on top of each other. Really good, because 4D orbitals are somewhat a little bit more extended. Now, this is for elemental solids, actually. It's not for oxides, elemental solids. Now, if you look at the 3D elements, just elements, then you see that DFT has a slight overbinding. So the total energy of DFT, so cross is experiment. So crosses are here, and experiment is slightly lower. So DFT slightly overbinds in 3Ds. However, when you go to 4Fs, then you see that basically this total energy versus band occupancy is completely flat. And that's indication that basically the size of the unit cell, the first approximation, doesn't care about the filling. So within DFT, you always get this U-shaped curve, always, no matter what, because we bind strongly here. But in lanthanides, you see that this curve is flat, except there are some peaks in particular valencies where you have very strong multiplet effects. Okay, so this you cannot predict at all. You cannot predict at all with DFT. This is very bad. Now in actinides, however, there is a reasonable agreement with DFT for this part, this down term, but then around plutonium it jumps, and here you have more or less localized behavior. So in F systems, the DFT has difficulty to explain, but at least in 3D and 4D it's pretty good. Now, what about the oxides? Well, in oxides are typically more correlated than elemental solids, isn't it? So I took here one well-known example of a cubic perovskite, strontium VO3, in which correlations are pretty substantial. So I think I already showed at one point that the LDA bands are those in this green color, and then the experiment is renormalized for between factor of 2 and factor of 3. So the RPS data is here. Okay. However, the question is, how good is the structural prediction? Clearly, the band structure is not so great, but is the structure reasonable within DFT? Well, if you look at it, LDA typically underestimates the volume. PBE usually overestimates the volume. And it turns out, however, if you take PBE sol, then it's pretty close. Okay? That's the message. So the point is that even though the band structure is not very good, the structure is pretty decent. Okay? So therefore, in some sense, we have a hard job. In our beyond DFT, we want to correct spectra, but we should not make the structures worse. Okay? Naively, you would say, well, once you correct spectra, structure is also going to be corrected. But in this case, you don't want to correct it, okay? Because it's already very good. So, however, if you look at another system like multi-insulating FEO, then the agreement is much worse. So if you look at the non-magnetic FEO, you see that within DFT, LDA underestimates, PBE underestimates, PBE sol. They're all very, very, very far from experiment. Experiment's here. Okay. Then, if you do this calculation in the antikinetic ordered state, then it turns out that PBE actually comes somewhat close to experiment, but it's still not correct. But of course, PBE, it's supposed to underestimate the volume normally, but here it overestimates the volume, but here it underestimates. So this is somewhat troublesome, isn't it? So FEO is very, very bad. So the question is, can we consistently improve energies and spectra of correlated solids? Okay, and that's what we work with Turan Birol, when he was at Rutgers, we worked on this problem, and Turan found that actually this indeed works. So first, strontium VO3. What happens in DMFT is that bands are normalized, as we said, for a roughly factor of 2 to 3. Okay, so the spectra looks much better. So coated metal. And when you look at the structure, LDA underestimates, PBE overestimates, and then DMFT is almost on top of PBE Sol. Okay, so I would say this is as good as the best DFT functional that we can get. So we are not making it worse in correlated solids, correlated electrons. Yes, so in order to get this good agreement, we are using LDA plus DMFT, especially because we know how to subtract the double counting within LDA plus DMFT. Okay, other functions are more tricky because they are not obtained in such a simple way from the electron uniform electron gas. But yes, indeed, I mean PBE is problematic. Why? Because you see in LDA the bands are too broad, but at the same time it overbinds, and that's how what it should happen, isn't it? So the kinetic energy is overemphasized within band structure methods. So the bands are too broad, and at the same time, or quasi-particle is too broad, let's say, and at the same time it overbinds. Okay, and then it's relatively easy to correct. Okay, but if you have GGA where the structures, where the volumes are too big already, and at the same time the spectra is almost identical, that's much more tricky to correct. And in principle, if you had exact double counting for GGA, then it might be able to correct that. But we have double counting for LDA, actually. Okay, so equation of state is pretty good. Now, what about the iron oxide? Well, LDA, PBE, PBE Sol, pretty bad. But if we do DMFT, even in non-magnetic state, we get a curve which is centered very, very close to experiment. Okay? Now we do this in the ordered state. Again, ordering doesn't do much in DMFT, okay? Because you already have local moments, okay? So this local moments order, but that doesn't make a big difference in structure. And indeed, that's usually the case in experiment. So now if you look at the equation of state a bit more carefully, this is LDA plus DMFT free energy for LDA plus DMFT. You take the derivative of this, you get the equation of state, pressure versus volume, and then you look at the experiment, and actually it's pretty close to that. Okay? So the important point here is that within DMFT, of course, this has very large fluctuating moments, and these fluctuating moments have pretty large entropy. So the entropy here, well, at high temperature is log 6, but then it goes down a little bit. So at 300 Kelvin, it's of the order of 1.6 something. Okay, so pretty large entropy is stored in these fluctuating moments. Now, while these systems can be reasonably well described with some DFT or DFT plus U, usually people try DFT plus U, although iron oxide is probably one example where it's hard to do it even with DFT plus U. But many systems can be kind of done with some mean field type of method. Now, cerium is a typical example where you can't do that. Cerium volume collapse is actually a big challenge for most band structure methods. Why? Because it has this first order transition from alpha to gamma phase, and that's very hard to account for in any method that doesn't take into account Kondo screening. So within DMFT, of course, we can easily change the volume, and we can see that in gamma phase, there is no quasi-particle peak, so this is so-called incoherent state or local moment state. But when we are in the low temperature phase, the spectra function has very clear quasi-particle peaks, which turns out to split into so-called 5.5 and 7.5 peak. But the important point is that very strong quasi-particle peaks. And the question is, what happens with the structure when you look at the feedback effect of this strong change with volume of the spectra? How does this influence the structural properties? And yes. The absence of yes, yeah. Actually, it turns out that this type of work was done way before DMFT. So it's a so-called Kondo volume collapse mechanism that was figured out by Jim Allen way before the DMFT. And actually, they fitted this to just impurity calculation. They had single Anderson impurity calculation, and they adjusted parameters in such a way that they got pretty good agreement with the experiment. And actually, when DMFT came around, then they realized that actually they were doing some pre-DMFT things. Just looking at the ARPES, they figured this out. So it has a long history. Okay, so this was understood, as I said, that at least phenomenologically has to be an Anderson impurity type problem. Okay, so now if you look at the free energy, what happens? Well, at 400 Kelvin, at a high temperature, free energy doesn't show any sign of transition. But if you go to 400 Kelvin, you see the free energy has this funny slope here, which seems to be slightly wrong, or it's almost constant. Okay? When you take the derivative, and why is that? Well, because the entropy changes a lot. So the entropy changes from almost nothing at small volume, because you have very good metal, and then when the system goes into so-called localized moment regime, then you have a huge entropy of the order of 1.6. So this entropy change, then if you put it into free energy, you will see that there is a huge change of slope. And then when you take the derivative of this, you see that there is a very flat region in volume where the first order transition occurs. Okay? So this is experiment, this is theory. So they are very good, well, very decent agreement. And what's important here that if you look at the other functionals, so LDA, PBE, PBE sol, you see none of those functionals has any indication of this wrong slope, or very, very, let's say, very linear slope here. So the DMFT clearly has an indication of the mode transition. All the others don't have, doesn't it? So that's something that you cannot explain with any other functional. Now, yesterday we saw a lot of those plots for magnetic susceptibility. Basically, this is what neutrons measure, okay? And I just want to show you that this is something that we can also calculate within DMFT, okay? So how is this calculated? Well, we need to calculate the so-called two-particle vortex function from the impurity within DMFT, so which means that you obtain the irreducible vortex function from the impurity, and then you address it with so-called beta-salpeter equation to calculate magnetic susceptibility or any other susceptibility. And here are examples for iron superconductors. So barium iron 2 arsenic 2, lithium arsenic, FeSZ. And the important point is that what happens in these superconductors is that they have this pretty large blob of spectra near pi 0, 0, pi. Why? Because they're close to magnetic instability. But nevertheless, if this intensity here is not extremely sharply peaked, they will not go through the superconducting transition, because this becomes just very strong, but not strong enough to go to the charge order phase. And many times it shifts a little bit to incommensurate Q. It's not exactly commensurate. But the question, however, that I want to ask here is that when you have a state such as that, which has a lot of this incoherent spectra, isn't it? Either in a single particle spectral function, you can look at it, it's pretty incoherent, or in two-particle spectral function. The question is, what happens with the structure? Okay? Yeah?
There is a large number of people in this field who produce field fluctuation theory.
Yes?
Is there any way within that other process to get it into field in a reasonable way?
Well, yes and no. I mean, the trick of the spin fluctuation theory, if you want to get decent spectra or similar spectra, you need to go into the ordered state. So you need to go into the mean field state. You have to tweak the amount of the long-range order, and then somehow you get some reasonable spectra. There were some papers where they produced reasonable spectra. Okay, but of course you have tuning parameters.
Is it true that in those approaches, this origin of the coherent is completely different?
Completely different. Exactly. In the ordered state, these are interpreted as magnons, but here are paramagnons. So that's the difference. So this is this ordered state. So therefore, all these things are paramagnons. These are very, very similar to what were shown by Colin Broholm. He was also looking at the paramagnons in most systems, disordered state, isn't it? This is disordered state. While if you go into the ordered state, then it becomes much more sharper. So within spin fluctuation theory, you would get maybe similar spectra, but it's going to be much, much sharper because they're going to become real phonons, real magnons. Sorry, not phonons, magnons. Okay, magnons. But here they're paramagnons. Okay, so yeah, that's hard to get within any other approach because you have to take into account local moments if you want to get that. Okay, so now the important point is how does this, what is the influence of this incoherent spectra to so-called, to structure? And one important quantity is electron-phonon coupling because these are superconductors. So people are very interested in electron-phonon coupling in fluctuating moments. And the interesting thing is that within DFT, electron-phonon coupling in many of the systems, which are quite covalent, turns out to be not so good. Okay, so the DMFT electronic states are much more sensitive to selenium displacement than predicted by DFT. So here in this iron superconductors, you have a layer of iron and you have another layer of selenium. Okay, and then the question is when you displace selenium, what's the change of the spectra? Or in other words, how big is the electron-phonon coupling? Isn't it? Because the electron-phonon coupling is basically the amount of change of the band structure by displacing an atom a little bit. This is called deformation potential. Now, it turns out that within better theory, like DMFT, this sensitivity of displacing selenium is much, much stronger. Okay? And it's easy to understand why. Okay? So it's kind of feedback effect of correlations. So first, it turns out when you do beyond DFT method, you will immediately see that if iron becomes more correlated, then selenium will move away from iron. Okay, you can see this effect even in DFT plus U. Okay, in some sense it's taken into account even by Hartree. But of course with DMFT you can predict the selenium position much better. Okay, so in other words, selenium moves away from iron because of correlations, because iron starts to become bigger because electrons are more localized. Okay, selenium moves away. But now that selenium moved away, hybridization is decreased, doesn't it? So hybridization between iron and selenium decreased. So therefore iron becomes even more correlated, doesn't it? Correlations are stronger then, okay? And that pushes selenium even further away. So that explanation that there is a positive feedback effect, okay, immediately tells you that the effect has to be big. It's not small, doesn't it? And indeed, the effect is pretty substantial. So now, in terms of numbers, here you see band structure. So these lines here are how much the band structure changes within DFT, and the scalar coding here is how much the band structure changes within DMFT. And you see this arrow here is much bigger than this little arrow here. Now, of course, one needs to do a calculation just for all possible Q points and for all possible pressures, for example. And here's a calculation for the so-called deformation potential. Deformation potential is again exactly what I said here. Is how much the bands move, bands at the Fermi level move when you move selenium. So it's in units of eV per angstrom. Okay. So this deformation potential as a function of pressure. You see this is prediction by DMFT, and this is prediction by DFT. Okay. So huge difference. And now, why is this important? Because this was actually measured very recently by Zheng Shen group in Science 2017. What they saw is the electron-phonon coupling in their experiment on iron selenium is actually -13 plus minus 2.5. That's their estimation. This is very, very complicated pioneering experiment. It's probably one of the first, as far as I know, it's the first one that measured directly electron-phonon coupling in solid, in any solid. So their point is that it's around -13, and the prediction in 2014, a couple of years ago, was that it's between -10 to -13, pretty close, okay? But now if you look at the DFT, you see that it's almost 1 order of magnitude smaller, okay? So in other words, this was not just lucky guess by theory, but actually turns out that we managed to predict it. Yes?
So in the case that the bands are not perfectly coherent, how
Yes, I mean, these are not that, I mean, at the Fermi level, these are metals, and therefore you do have well-defined quasi-particles, yes. But if you don't have well-defined quasi-particles, that's a different story, yes. Thanks. Yeah, so in addition to electron-phonon coupling, of course, the position of selenium is much better, and also the frequency. The frequency is closer. But the important point is that this incoherence actually has a lot of strong effect on the structure and on the electron-phonon coupling. Now, we discussed a lot about structure, but I want to give you some insight of how to calculate free energy and its derivative for generic solid. So we started with functional gamma of g, and we wrote it explicitly down. That's the explicit expression for our functional. And then the question is, how do we calculate all the terms? Now, in principle, most of people in this field actually calculate not the free energy functional, but they calculate total energy, so-called total energy, with Migdal-Galitsky formula. And now it turns out that Migdal-Galitsky formula works when you have so-called conservative approximation. But DFT, it's not conservative approximation. So therefore, DFT plus DFT is also not conservative approximation, strictly speaking. So therefore, what you should do is you should actually evaluate this, this functional. And how do you do that? Well, the Green's function can be easily evaluated. Log of Green's function is easy to evaluate. Why? We just need eigenvalues of G. You have a Green's function, which is a matrix. You need eigenvalues, which turns out to be frequency dependent now, but you can evaluate them, isn't it? So these terms are easy to evaluate. This term is easy. This term is easy. The only thing that's hard is actually phi functional. Okay? In principle, it's doable because we know that we can solve the impurity problem, but still, the phi functional is not easy for Monte Carlo methods. So the idea here is that we actually look at the free energy of the impurity, okay? And then free energy of the impurity has the same phi functional in it, okay, as we discussed yesterday, isn't it? So this phi impurity and phi DFT are the same. So therefore, if you know the free energy of the impurity, the rest of the terms are also easy to compute, okay? So that's how you can then calculate phi. And so it means that free energy of the solid is the same as the free energy of the impurity plus the correction terms, isn't it? The correction terms which have to do the trace log G is different than trace log G impurity, isn't it? And then you have to add all the DFT terms, okay? So that's how you can calculate free energy of the solid in practice. And of course, there are some tricks of how do you calculate then F impurity if you have total energy. So that's kind of standard. Now, the fact that we have stationary functional, then this can be extremized. And moreover, one can take analytic differentiation of this functional to get force, doesn't it? And once you have force on all atoms, we can predict crystal structures. Now, why is this important to derive analytically? Because otherwise, if you want to make a finite displacement, if you want to calculate structure with finite displacement, you need 3 times n, where n is number of atoms per unit cell, of calculations, isn't it? That's very expensive. So you really want to have analytic expression that gives you force for each calculation of your band structure. So how do we do that? Well, first let me show you some example of how well it works. So again, I'm going back to rare earth nickelates, which I introduced a few slides back. So this is neodymium nickel 03, one of these rare earth nickelates, in which the high temperature structure is this PBNM structure. It's metallic. And then at low temperature, it undergoes this kind of bond disproportionation, which means that one nickel octahedra is much bigger, and the second nickel octahedra gets squashed a lot. And the question is, how well can one predict these structures? And then there's another structure, which is magnetically ordered state, in which the unit cell quadruples. So we have 4 of those here, 1, 2, 3, 4, and then you have certain arrangements of magnetic moments. Okay, so the question is now, how well do we predict the structure? And here are the so-called Wyckoff positions for all atoms in the unit cell. Okay, and experimentally, this structure was characterized pretty well with X-ray. Okay, Actually, it took for a long time before they figured out what exactly are those positions, but now they have pretty good confidence. It's not that easy, but it was done. And now we can predict, we can compare different theories. And first we start with GGA, of course. The troublesome thing here with the standard DFT is that DFT can predict, or GGA can predict pretty well this high temperature structure, but has no clue about this disproportionate structure, this insulating structure. Now, you can do GGA plus U and tune U to the best possible number, and then you can predict this structure reasonably well, but then you cannot predict the first structure, okay? So you can have either one or the other, and you have to change your functional to go from one to another. And if you look at the database of all materials in this materials project, you will see that they are constantly changing Q. So you have this particular structure, and you have this U. You have this particular structure, you have a different U. Okay. So why? Because well, you want to account for such a let's say transitions, doesn't it? So, but it's hard. So what you really want to have is a functional that can predict all of those at the same time. Okay. And so now let's look at the error compared to experiment. So position of atoms compared to experiment. In this paramagnetic phase of DMFT, the error is 5 × 10⁻⁻3, and GGA error is 2 is 2 × 10⁻². So in other words, the DMFT is around factor of 4 better, okay, in terms of structure prediction. The high temperature structure, this one, is factor of 4 better. Now, when you go to low temperature, you see the GGA plus U, where you have to change the functional, tune the U, it's still factor of 2 worse than the DMFT prediction, okay? And in DMFT, it doesn't matter so much whether you have long-range order or you don't have long-range order, because you have local moments already, so the two structures are actually extremely similar. While in GGA plus U, of course, you always need to have a long-range order. Without long-range order, there is nothing reasonable. Okay, so the important point is that then with single functional, you can predict the existence of all 3 states. Okay, you don't need to tweak the functional for each case. And now if you can predict with the same functional all 3 structures, then you can draw a single line as a function of distortion. You call it distortion. You linearly interpolate from the undistorted structure to fully distorted structure, let's say. Okay, and you look at the free energy as a function of the distortion index. Okay, and then you can see that at high enough temperature, let's say 200 Kelvin, you have just a single minimum, and this minimum is actually the high temperature metallic state, isn't it? Then, and it has the spectra like that. Then you start to reduce the temperature, and you see that at 100 Kelvin, actually you see local minimum, okay, which is still metastable because this energy is much lower, isn't it? So this state is actually metastable, but it exists. So it has a very clear gap. It's a paramagnetic Mott insulator, isn't it, with a gap. But the important point is that it's metastable. Okay. Now, without the forces, it's very, very hard to calculate this metastable phase because it's actually, it's just a little minimum at this temperature. Of course, this minimum will grow with reducing temperature, but still, if you don't predict the structure very, very well in this minimum, you're going to be blind to it. There are too many degrees of freedom to tune, isn't it? Lots of internal Wyckoff positions. Okay, so yeah, here you can get this local minimum, and then you can allow for the long-range order, and then you see that actually magnetism reduces the total energy quite substantially. So you can get the second minimum to be more stable. So now how is this done in practice? Now this is cool, and we want to understand how do we calculate the force. Well, the first attempt is actually pretty trivial. We have your functional gamma, and you want to take the derivative with respect to position of atoms in itself, isn't it? So that's the force. It's the derivative of energy with respect to displacement. Okay, so how do you do that? Well, you can take the derivative of gamma with respect to g at constant position of ions times the derivative of g with respect to displacement of ions, okay? Plus the derivative of energy with respect to displacement of ions at constant g. That's the usual way we can differentiate, isn't it? The total derivative and the partial derivatives, okay? Now, since the functional is stationary, as we discussed, then this derivative with respect to G at constant ionic positions should vanish, isn't it? That's what we were told. Okay? Well, if it vanishes, then we have a very simple life. So all we need to calculate is then the derivative of this gamma at constant G with respect to R. And then you look at the functional here, well, which part that depends on R when you have constant G? Well, this one doesn't. This one doesn't. So G0 depends, and E nuclear depends, doesn't it? Well, that's very easy then. So all you need to do is to differentiate E nuclear, and then G0, which has nuclear here, you do this, and, well, you end up in Hellman-Feynman force. This is what is called Hellman-Feynman force, okay? So life is really simple. Is this correct? So this calculation, naive calculation says, well, you actually don't need to do anything. DFT, you just take Hellman-Feynman force, which is already implemented in DFT, and that's it. Well, it's not true. So this is wrong. This is wrong. So why it's wrong? Well, because the DFT people will immediately tell you this is correct only if you have originless basis set. So if your basis set is like complete basis set written in plane waves, okay? If you have a plane wave basis set which doesn't have any origin doesn't move with atoms, then only Hellman-Feynman force contributes, okay? However, if you have a basis set that is atom-centered, okay, then when you move the atoms, you move your basis, okay? Your basis moves with an atom, and that creates a substantial force. It's so-called Haule force. It's a force because of moving your basis, okay? That's an extra contribution to force, and it's not small. It's actually large. And now you can think of it, is there any way that I can get rid of this force altogether? So Haule force. Can I have a way of implementing DMFT in which the Haule force would vanish? And my answer is no, you can't. Why? Because you always need a projector to localized orbitals. These localized orbitals will always move in an atom. Okay? So projector moves with an atom. And as soon as you have an orbital or any set of orbitals that are moving with atom, it immediately creates Haule force. Okay? So therefore, you would always need to calculate this force much more carefully. You cannot just rely on the fact that the functional is stationary. You have to calculate the force, so which means that you need to differentiate the implemented expression for the free energy very, very, very carefully. Okay? And that's kind of painful. People have done it in the past for DFT, but for DMFT, this is pretty new. And now, why is this important? Well, the important point that I want to convey here is that you don't have the second derivative of phi functional with respect to G in this expression. Because naively, look, we need to take the derivative of this functional with respect to G twice, okay? And therefore, naively, you would say there are going to be terms which will be derivative of the self-energy with respect to G, okay? And this is two-particle vertex function. That's extremely hard to calculate. Now, if such terms remain in the expression for the force, that's extremely hard job. But because of the stationarity, such terms have to vanish. I can prove that, okay? I can prove that, because in principle, if one could use complete basis set originless, then these terms should vanish. So therefore, the corrections that we should get should only have so-called basis set corrections. Basis set corrections. Okay. Now, how do we do that then in practice? So first, we look at the functional gamma of G, and then we have this expression. But now we can, in order to calculate the free energy, we can insert the solution of the Dyson equation. So we always satisfy the Dyson equation. Therefore, we can insert this G0 inverse minus G inverse. We can insert this expression in here if we want to, doesn't it? And that's the free energy expression that we actually use, okay, in the calculation. So I just inserted G0 inverse minus G inverse, which is hard 3 plus so on and so forth. So we have this term, trace V Hartree plus V exchange correlation times rho, and then I get this trace sigma impurity V double counting times G log. That when I insert this. Okay, so that's the free energy, and that's the functional that we actually need to worry with respect to R. Well, in addition to this, we need to add nuclear term, which is just a number, isn't it? And we need to, because we're adding, we are working at constant n, we need to add nu times m, because this expression is usually at constant chemical potential. And then what do? Well, we have to implement trace log G, for example. So in order to implement trace log G, we need to solve so-called, well, we solve for the eigenvalues and eigenvectors, isn't it? This is just an expression for the eigenvalues, epsilon k, which are now omega dependent. Why? Because we added self-energy. So we have self-energy, isn't it, which we embed here. Then we add all the DFT terms, and we see that this now defines the eigenvalue of the Green's function. These are eigenvalues of the Green's function. Then this gives us the Green's function. The Green's function is now very easy. It's just 1 over omega plus mu minus eigenvalues, of course. And then it's easy to calculate trace log G, because it's just a simple expression in terms of these eigenvalues. So now we have free energy, which is slightly easier to calculate, doesn't it, with these eigenvalues. And now we can start to take derivative of this. Okay? So when you take the derivative of this first term with respect to displacement, so what you need to do is you take the derivative of these things, which 1 over this, isn't it, because it's log, 1 over this, times the derivative of epsilon k minus mu. So both epsilon k and mu can change when you displace an atom, isn't it? So that's the derivative of this first term. Then you have to take the derivative of these two terms, for example, and then one term here will cancel, okay? Which one? Well, when you take the derivative of E Hartree plus E exchange correlation with respect to displacement, you can, this is a function of rho only. So therefore, you have a chain rule. Take the derivative of this with respect to rho times derivative of rho with respect to R, and therefore, it cancels one of the terms in here, okay? So these two terms contribute only one term, which is rho times the derivative of V with respect to R, okay? So then you go to this term, you get the derivative of E nuclear with respect to R. Mu n, we are staying at constant n, so therefore we have only d mu over dr. Then this entire term, again, there's a lot of cancellation going on because the phi is functional of G only. So therefore, when you take the derivative, you always take the derivative of phi with respect to G times derivative of G with respect to R. Okay. So therefore lots of terms here cancel. And then, well, this n delta mu here cancels, of course. Then what else? So we're combining these terms together. V Hartree plus V exchange correlation can be written as V contra minus V nuclear. Right? So then we also know what are the Hellman-Feynman force. Okay, so we substitute this back, and then we realize that this term and this term is exactly Hellman-Feynman force. So we have some corrections to Hellman-Feynman force. Okay, and the expression for the correction is this plus this plus this. So there are three terms which are Hellman-Feynman forces. Okay, these three terms. Now, if the basis set is originless, then these three terms should exactly cancel. Okay, and indeed there is a lot of cancellation going on. That's what I want to prove. So what I wanted to prove you is that derivative of self-energy with respect to G will not enter. Look, here we have derivative of self-energy with respect to R. Okay, when you see a term like that, it immediately you ask yourself, do I need derivative of self-energy with respect to G, then derivative of G with respect to R? Naively, you would say yes. So we need delta sigma. We need to know how sigma changes when you change the atom, when you move the atom. Okay? So that's complicated because you need to calculate impurity problem for each position of atom, isn't it? Or you would need to take the derivative of self-energy with respect to G and derivative of G with respect to R. Now, derivative of sigma with respect to G is so-called two-particle vortex function. That's very, very hard to converge to high accuracy. Okay? Now, however, the point is that d sigma over dr exists in this term, and it also exists in this term. Why? Because these eigenvalues contains sigma as well, self-energy as well, doesn't it? These are the eigenvalues including sigma. So therefore, d sigma or dr appears in here, and you see that there's a minus here, so therefore they're going to cancel. They have to cancel, okay? So d sigma is very hard to compute, but it cancels out, okay? So that's because function is stationary. It has to cancel out. Now, to see this much more carefully, one can go through this derivation a little bit more carefully. Basically, maybe that's too much. I can skip this. But basically, if one writes down this expression, how epsilon, so this expression for epsilon k, you can then differentiate the entire expression for epsilon k, isn't it? And you get the derivative delta epsilon k. So we need to know how delta epsilon k changes. And if you do that, you see that basically delta epsilon k has a term which looks like delta sigma, okay? And that's sufficient to prove that delta sigma will drop out of the force, okay? Sorry? Which factor? Yes, so this 1 over omega actually is exactly g log, okay? So if you look at it carefully, this and this g log is exactly the same thing. So they cancel together with prefactors, yeah. Okay, so therefore the final expression is that you have the Haule forces which have this contribution. So these terms look more or less like DFT terms, except that the density matrices are slightly different than in DFT. So the density matrices are much more complicated, but these terms look like DFT terms. And there is the extra term which is really new. It's DFT-like, and this term actually is just the derivative of the projector. Okay, so it's very easy to understand. It's self-energy correction. It doesn't contain the derivative of self-energy, but just self-energy correction times the derivative of the projector with respect to our displacement of the projector, how the projector changes. So, and this is actually not hard to implement. And so the important point is that force does not depend on the derivative of sigma with respect to g, which is the two-particle vertex function, and it also doesn't depend on phi itself. So in this sense, it's better than free energy. So free energy depends on phi, but the force does not depend on phi. Phi is hard to compute as well. So the force depends only on the self-energy itself. And that's a quantity that's very, very easy to calculate within quantum Monte Carlo. So this is a beautiful thing for quantum Monte Carlo. It's really easy to calculate. And so just to convey this message that this is really the quantity that's easy to compute, I want to compare here here we have a number of iterations, and we are comparing free energy, calculating it in two different ways. So we can calculate free energy directly from our Monte Carlo data, and you can see that free energy after a few iterations start to saturate, but it still contains a fair amount of noise of the order of 1 millieV was its iterations. Here it's more or less converged, but it has a noise. But then if we calculate the force, okay, the force has much smaller noise, and moreover, we need to multiply force with the distance, the typical distance in which we move the atoms. And then this expression, which is equivalent to this, actually just shifted away, but otherwise there should be the same number. So this noise for the free energy has a much, much smaller noise, way smaller. So it's almost like more than 1 order of magnitude smaller noise. So in other words, the free energy is now easier to compute with forces than without forces. Okay, which is kind of counterintuitive, but this comes from the fact that the quantum Monte Carlo is really good at calculating self-energy, and it's not so good to calculate the phi functional or to calculate the second derivative of phi functional. These are very hard objects to calculate. Okay, so thank you very much.
So we have time for maybe a couple of quick questions.
Currently, this code doesn't work yet for this case. But yes, I mean, basically, when you want to calculate, for example, force, isn't it, or spin or electron phonon coupling, and you have presence of spin overcoupling, you have to add to the Hamiltonian this term, the spin overcoupling, and you have to take the differential derivative with respect to that. Now, this is not implemented even on a DFT level within Win2K. Okay, so I'm thinking of doing this, but I didn't do it yet. So no LAPW code, as far as I know, has that yet. WASP, I think it does. Yes, but any other all electron code doesn't have that yet. But in principle, there is no problem.
So you mean forces with superconductors?
Yes.